This is problem 14-86. It's on page 759. Air enters a 40 centimeter diameter cooling section at 1 atmosphere, 32 degrees Celsius, 70% relative humidity at 120 meters, meters per minute. In other words, that's the velocity. The air is cooled by passing it over a cooling coil through which cold water flows. The water experiences a temperature rise of 6 degrees Celsius. The air leaves the cooling section saturated at 20 degrees Celsius. Determine A, the rate of heat transfer, B, the mass flow rate of the water, and C, the exit velocity of the air stream. So let's go ahead and sketch this. Here's the duct section, and cooling water is flowing through a coil such that the temperature of the water rises by 6 degrees Celsius. So there's some heat transfer rate out of, out of the section into the water, basically, effectively, by this temperature rise. That is right. So state 1, state 2 will be at the entrance and exit, respectively. Temperature at the inlet, state 1, is 32 degrees Celsius. The relative humidity at the entrance was given as 70%. The velocity at state 1 was given as 120 meters per minute. I went ahead and converted that to meters per second. Of course, it's just 2 meters per second. I won't go through those details. The diameter was given as 0.4 meters. I went ahead and calculated the area since I knew I would need it. Just pi d squared over 4 came out to about 0.1257 square meters. And then the temperature at the exit was given as 20 degrees Celsius with a relative humidity of 100%. Now, we don't know if any water is condensing out of this or not, but we will be able to find it out. So the first thing I'm going to do is use the information that's been given to me to find out the state of the system coming in. So I'll just read off from the psychrometric chart the specific volume. I got about 0.894 cubic meters per kilogram. Read off the enthalpy. I got 86.5 or so kilojoules per kilogram. The absolute humidity, I got 0.00212 kilograms of water per kilogram of dry air. The specific volume at the exit, since I've again got two pieces of information, I can look up anything I want, is 0.851 cubic meters per kilogram. And I just read all these off the psychrometric chart. The enthalpy, 58.1 kilojoules per kilogram. The absolute humidity, 0.00149 kilograms of water per kilogram of dry air. Now, notice something interesting here. Notice that the absolute humidity has decreased. How is that possible? Well, the only way that could have happened is if some of the water condensed out of the air. In fact, the author gives it away by asking the questions, find A, the heat flow rate out, Q dot, B, the mass flow rate of the water. So there is going to be water flowing out of this. And then finally for part C, what's the velocity at the exit? Basically the purpose of part C is to make us use a mass balance along the way. All right, so to start this off, I'm going to begin with an energy balance. So let's see, Q dot, the heat flow rate out, will be equal to the mass flow rate of the air times the enthalpy change of the air. Understanding that the enthalpy coming in state 1 is more than the enthalpy in state 2, I just wrote H1 minus H2. Now, we need the mass flow rate of the air. It looks like we won't use it again, so I'll just go ahead and substitute for it. So the mass flow rate of the air can be written as the density at state 1 times the volumetric flow rate at state 1. And let's see, H1 minus H2, just continuing with the equation. And to write down the volume flow rate, that would be the same thing as the velocity times the area. And then instead of using density, I'm going to use specific volume, since that's what I have at state 1, which is just the inverse of density. So that takes care of the mass flow rate of the air and writes everything in terms that we have. In fact, the velocity is 2 meters per second The area I calculated as 0.1257 square meters, specific volume 0.894 cubic meters per kilogram. The enthalpy change was H1 minus H2, 86.5 less H2, 58.1 kilojoules per kilogram. Let's see what happens with the units. The kilograms go away. We've got meters times meter squared is cubic meters, so that cancels. And we've got kilojoules per second as our units, which is a good thing. That's what we should have. When you plug it all into your calculator, you get 7.9840 kilowatts, so kilojoules per second. So there, it's about 8 kilowatts or so. I'm going to round that off to about 8 kilowatts. That's the heat flow rate out of the system. So this is a pretty good size chiller. Now, we want to find the mass flow rate of the water. So we can write an energy balance based on what's happening, should be the mass flow rate of the cooling water. I was thinking of the mass flow rate of the water vapor that's condensing out of the air. That's not what they asked for. They wanted the mass flow rate of the cooling water. So let's go ahead and do that. If this is the heat flow rate out of the air, that heat has to flow into the water. So the mass flow rate of the cooling water times its heat capacity times its change in temperature would equal the heat flow rate out of the air. All this heat from the air and the humid air has to go into the cooling water. Now we know the temperature change of the cooling water, so we can calculate the mass flow rate of the cooling water by rearranging the equation. We just have Q dot divided by Cp delta T. Now the, let's do it this way. So the heat flow rate we know is 7.9840 kilowatts, or in other words, let me substitute kilojoules per second. The heat capacity of water is about 4.18 kilojoules per kilogram per Kelvin, or per Celsius, it doesn't matter. And we know we have a 6 degree Celsius change. Now I don't have to change this 6 degrees Celsius to Kelvin because it's a temperature change. And so since it's a temperature change, it will cancel with the Kelvin there, and kilojoules go away. We'll have kilograms per second. I'm going to jot down the mass flow rate of the cooling water over here. It comes out to about 0.318 kilograms per second as the required flow rate of the cooling water. Now how about the velocity of the gases coming out at the exit? All right, well, the mass flow rate coming in, as far as the air is concerned, is equal to the mass flow rate coming out. So let me change my notes just a little bit. So the mass flow rate of the air in 1 is equal to the mass flow rate of the air out at 2. Okay, so if we were to write that the velocity times the area at state 1 divided by the specific volume is the mass flow rate coming in at 1 of the air, then we could equate that to the velocity and area and specific volume at state 2. Now be careful here. This is only true for the mass flow rate of the air. The mass flow rate of the water is not the same. As I've discussed, some of the water is going to trickle out. It's going to form droplets, and it's got to come out somewhere. I didn't draw it here, but it's going to condense out because we know that the absolute humidity has dropped. And so, now, another thing, don't be confused between the mass flow rate of the cooling water and the mass flow rate of the water vapor that's condensing out and coming out of the airstream. But the mass flow rate of the air at the entrance and exit are identical. Now the area is the same, the velocity is the same. Now it doesn't matter if we're talking about the velocity of the air particles or the velocity of the water molecule. It doesn't matter, right? They would have the same average velocity going through this cooling section. However, the specific volume is what makes this work, because this specific volume is per kilogram of dry air. Let's look at the units. The velocity would be meters per second. It doesn't matter if we're talking about air or water. The area is the same, right? Air and water flow through, in other words, water vapor, flow through the entire cross-sectional area. So the whole numerator couldn't care less if we're talking about water or air. The denominator, though, has units of, let's see, cubic meters, so volume, per kilogram of dry air. So look what happens. The cubic meters go away, and we have kilograms of dry air per second. And that's why we use the air as the basis, so we can do things like this. Anyway, so that's why in the chart, this specific volume is per kilogram of just dry air. Okay, it's the same thing over here. All right, so anyway, since the entrance and exit areas are the same, I can cancel that and simply calculate the volume at the exit based on the volume at the entrance and the ratio of the specific volumes. Okay, so this is 2 meters per second multiplied by 0.851 over 0.894. Those are the specific volumes at the exit and entrance respectively. So now we can calculate the velocity at the exit. It comes out to about 1.9 meters per second. Okay. Now, notice that one thing happened that I did not anticipate. I should have looked at my solution a little bit more in depth before I started this, but I was thinking about the water that's flowing out, that's condensing out. How would we calculate the mass flow rate of that water? Notice it wasn't asked for, but we could calculate it. In fact, all we would have to do is write down a mass balance, right? Because the air that comes in carries water with it, the air that leaves carries water with it, but not as much because some of it condenses out. So we could simply say the mass flow rate of the water, let me use a subscript W, at state 1 equals, because that's where water comes in, the mass flow rate of the water leaving at state 2, but also the mass flow rate of the water that is, let's just call it condensate here, okay? So really, if what we want to do is find the mass flow rate of the condensate water, we should solve for it. So the mass flow rate of the condensate water would be equal to the mass flow rate of the water at state 1 minus the mass flow rate of the water at state 2, which makes sense. If some water flows in with the air here and doesn't flow out here, it must leave. Okay, so how do we write down this? Let's see, let me make this clear. How do we write down this change? Well, how do we deal with the mass flow rate of the water at state 1? Well, that's simple. We just write down the mass flow rate of the air and multiply by the absolute humidity at state 1. Why does that work? Well, this humidity is just kilograms of water over kilograms of air. This is kilograms per second, so we get kilograms of water per second. Okay, so the kilograms of air just cancels out. We can do the same thing with the second term, mass flow rate of air multiplied by omega 2. Now, along the way, I should have calculated the mass flow rate of the air. I've avoided it all along. I didn't do that in my solution. I'll leave that to you. Remember that you could get it from, say here, for example, there's the mass flow rate of the air. You've got all of that. You've got the velocity. You've got the area. You've got the specific volume. So getting the mass flow rate of the air is straightforward. I would do it, but I'm not carrying a calculator. But anyway, then you have mass flow rate of air, omega 1 minus omega 2. You've got omega 1 and 2, they're right here and here. You can get the mass flow rate of the air, so that's easy. And you could actually calculate the mass flow rate of the condensate coming out of this system. That's not something that was asked for in the problem statement, but it's definitely doable and a reasonable thing to do, of course. Like I said, I don't have a calculator. If I did, I'd plug in the numbers and give it to you, but I don't.